Hello, today let us solve some simple problem about hydrostatic force on submerged curved surfaces. So here's the problem. A semicircular 40 feet diameter tunnel is to be built under a 150 feet deep, 800 feet long lake as shown in the figure. Determine the total hydrostatic force acting on the roof of the tunnel. In the figure, we can see the projected area of our tunnel. It is semicircular and built 150 feet underwater. Now, let's turn it into its isometric view to better understand the situation. There. That is how it looks like when viewed isometrically. Now, the problem wants us to determine the total hydrostatic force acting on the roof of the tunnel. In solving this, let us assume that atmospheric pressure acts on both sides of the tunnel. But before that, let us turn our figure into smaller liquid block with the tunnel as the base border. There. Again, let us assume that atmospheric pressure acts on this side and this side of the tunnel. Since it acts on both sides, therefore we can ignore the calculation for atmospheric pressure. Now, let's start our analyzation through having our free body diagram. In having a free body diagram for submerged curved surfaces, we have to draw a liquid block enclosed by the curved surface. In our situation, we enclosed our liquid block with the circular surface of our tunnel and its vertical and horizontal projections. Now, let us start finding the hydrostatic forces acting on the vertical and horizontal plane surfaces as well as the weight of the liquid block. So this is the final free body diagram of our problem. As you can see, we neglect the atmospheric pressure since it acts on both sides of our tunnel. Since it acts on both sides of our tunnel, it will result into zero resultant. Now let's proceed to our solving. First, let us solve the horizontal force on vertical surface, each side. This side and this side. Since the tunnel is symmetrical, the result of this side will also be the result of this side. So starting with the horizontal force is equal to the force acting along x. We all know that force is equal to the average pressure times the projected area of the system. Pressure in water or gauge pressure is equal to the density times the gravitational acceleration times the distance to the force's point of application, which is the centroid. So our formula becomes ρ times g times h times the area. In finding hc, we need to add the distance from the surface of the water to the top of the tunnel plus half of its radius. So it will go like this. S stands for the distance from the water surface to the top of the tunnel. So this one. Then add it to half of the radius of the tunnel. So this one. So it is the height from the surface to the centroid of the liquid block. So the equation will become like this. Ρ times g times s plus r over 2 times a. Now let's plug in the values of our variables. The ρ, which stands for the density of the water, is equal to 62.4 pound mass over cubic feet times 32.2 feet per second square, which represents g, the gravitational acceleration, times the values of s plus r over 2, which is 130 feet plus 20 over 2 feet. times the area of the half of the liquid block, which is 20 feet times 800 feet. Since the English unit of force is pound force, let's multiply it to 1 pound force over 32.2 pound mass feet per second square, in order for us to cancel all the units and left the pound force. Calculating the values, the horizontal force on vertical surface will be 1.398 times 10 raised to the power of 8 pound force. And this is the force on each side of the tunnel. Next is, we will find the vertical force on horizontal surface, which is the surface. So we will calculate this specific force, which is the average downward force on this horizontal surface. So again, we will use the force equation, which is this one. Now, this time, HC will be the distance from the surface of the water to the top of the tunnel. Because look at the diagram. All the red arrows are pointing on the center of each side of the liquid block, and Fy is pointing directly on the highest point of the tunnel, which is also the center of the horizontal surface. So that is our basis for the HC. Now, let's plug in the values. Same as what we did with the Fx, just substitute the values of ρ and g times the volume of water above the liquid block, which is 130 feet times 40 feet times 800 feet. So above this part, then multiply the 1 pound force over 32.2 pound mass feet per second square to cancel the units. Calculate, and it will result to 2.596 times 10 raised to the power of 8 pound force. That is the vertical force on horizontal surface. Now let's go with calculating the weight of fluid block on each side within the control volume. In doing this, let's use the usual equation in finding weight, which is weight equals mass times gravitational acceleration. Since we're dealing with fluid, let's convert mass into density times volume, turning the equation into ρ times g times v. Now, in finding the volume of this water, we need to multiply 800 feet length of the tunnel times this part of the water, which can be get through subtracting the area of the square to the area of half of the semicircle. Now, let's start plugging in the values of our variables. The density times the gravitational acceleration times the volume of this part of the liquid block times this conversion. Calculate the values and it would result to 4.285 times 10 raised to the power of 6 pound force on each side of the tunnel. Now let's put all the results of our previous computation. Through this, we can now solve the net hydrostatic force acting on the roof of the tunnel. Now, let's solve for the net downward vertical force Fv. In solving this, we need to add the Fy and the weights from the two sides of the tunnel. Substituting the values of our variables there. After that, let's calculate the values and it would result to 2.64 times 10 raised to the power of 8 pound force. So that is the net downward vertical force acting on the roof of the tunnel. Now, let's solve for the net horizontal force acting on our system. Since the horizontal forces are acting on the right and the left side of the tunnel, we will just cancel them since they are equal and opposite. Therefore, our total hydrostatic force acting on the roof of the tunnel is the result of Fv, which is the 2.64 times 10 raised to the power of 8 pound force.